Hello and welcome everyone. Thank you for coming. Today we have the pleasure to listen to Ayush Dixit, who is going to talk to us about underlying dynamics of sneezing. The floor is yours.
Thank you, David. Yes, today I will talk to you about underlying dynamics that is involved in sneezing. So before going ahead, let me thank all of the collaborators that I have. It includes people doing theory, like Detlef, Alex, people doing experiments like Alvaro, Tommy, and Prashant, and the people doing also doing numerics like Vatsal, Stefan, and Tunai. So before I go ahead, let me show you what happens when, let's say, if you sneeze. So this is you emit a cloud of droplets that comes out of your mouth. This all happens in roughly milliseconds. And if you are sick, then these droplets will have pathogens and viruses, and these droplets will stay. They will stay there for a long time, and the next person sitting to you will inhale it and become sick. So, first question that we want to ask is, where do these droplets come from? There are three different places. It's like a trachea, that is our air pathway, just deep inside of the lung, where the droplets are produced by like the flow of these alveoli structures, which creates the droplets, and then from our mouth. So during these violent respiratory flows, such as coughing or sneezing, it's mostly flow occurs in our trachea. In most of the recent reviews, they always predict that all of these breakup will happen, like Kelvin-Helmholtz breakup. So to check that, we made a cough machine, because we cannot visualize it when a person is sneezing. So we made a cough machine in our own group. So just like a normal person coughing, there will be an airflow. There will be a liquid layer which will get sheared, and we see that there are formation of bag-like structures, and there are like formation of jet-like structures. So essentially, there is a liquid layer of sheet which gets sheared as the airflow is happening. Now this doesn't look like a Kelvin-Helmholtz instability. So everything that we believe to be true for coughing and sneezing was wrong. And this is the most recent paper, the review paper in 2023. So whatever we believed about how coughing and sneezing were happening was wrong. And also in COVID pandemic, there were few questions raised. First question was, let's say if one person is sneezing, what is going to be the final droplet distribution of the cloud that we are emitting? And it turns out that it varies person to person. So every person has their different DNA, which changes the composition of our mucociliary fluids. It also depends on how many days you have spent after the infection has spread. It also depends on how old you are, and so many others. So physically speaking, there are so many different parameters that is going to govern the final droplet distribution that is going to have. So yes.
What is the geometry of this?
So
how is this?
So the dimension wise, this is roughly the dimension of our air trachea, and this is just a rectangular channel.
So you're looking at the top view,
and we are looking at the top view.
Okay, and so there's a film in this way, like a liquid film, liquid sheath.
So this is top view, and the liquid layer is on the bottom of the rectangular channel.
Okay.
So you put the channel like this, and you're looking from the top.
Okay.
it's half of your trachea, basically.
Okay.
So as a physicist, instead of looking directly into this complex problem, we start by breaking down the problem into smaller sizes. So first is that we see there are these jet-like structures which breaks into droplets, and there are then these bag-like structures which breaks into droplets. So we first only look into jetting. So it means the droplets that is coming from jet-like structures. So these are the things I will discuss for today. So on the menu today, I will discuss the droplets coming from jet-like structures and the breakup of the sheets. What is not on the menu today is the code that we use, which is Basilisk. So we solve the Navier-Stokes equations using one fluid formulations using volume of fluid. And all of the code that we have used and that I have used, it's freely available on our GitHub repository. So on the menu today, we have the breakup of droplet from a jet. To model this, we wanted to model this. We wanted to look for a simplified system where a droplet is coming from a jet, and we found it in a glass of champagne. So in a glass of champagne, we have lots of bubbles coming close to the surface, and they pop up and produce these droplets. But our mucociliary fluid is viscoelastic. So for that, we look into viscoelastic champagne. So we put inside of the Newtonian liquid, we put a different concentration of polymers, and we look into the bottom view. So in the bottom view, nothing changes a lot. All of them look the same. But in the view above the surface, there is a drastic difference. Even with 0.1%, 0.01%, we are able to suppress the formation of the jet. So this is, in a way, the result of first part going to be that when you increase the concentration of the polymers, you are going to suppress the formation of the jets. And through numerical simulation, this is what I will try to explain why and how this happens. First of all, for those of you who don't know what is viscoelasticity, so a medium which shows both viscous and elastic behavior is what we call viscoelastic medium. So when we talk about viscosity, if you have a fluid, you shear it, then the stresses will be dependent on the strain, like the rate of the deformation. If you have a solid, if you stretch it, then the stresses that is going to be generated is going to depend on just the deformation. It doesn't matter how quickly you do it, it just matter on the deformation that you have achieved. And the viscoelastic fluid, let's say if you put polymers inside of the liquid, it also depends on the strain rate and also on the strain rate itself. So it shows both viscous and elastic behavior. That is why we call it viscoelastic. So this is what the system we are looking for: a bubble cavity opened up. There are so many parameters that are varying here: density, viscosity, elastic modulus of the polymers, and the relaxation time. So we non-dimensionalize it and get the three independent parameters. First is Onezor, which we can think of as the dimensionless viscosity. Second is elastic modulus. So this is elastocapillary number. So this is elastic modulus over capillary pressure, which we can think of as dimensionless modulus. And third is Deborah number, which is relaxation time over process time scale, which we can think of as number. There is one more parameter bond, but we will keep it to the constant value of 0. So first, let us have a look into the Newtonian limits. In the Newtonian limits, it's just the Onezor or the viscosity that matters. So I show you three cases. I will be plotting velocity and viscous dissipations. So darker color will show you larger values. So I'm showing you three cases. So first case is, let's say, very small viscosity. So it's like, let's say, just it's a water system. And the third case is the very viscous case. So it's like a bubble bursting in honey or silicon oil. So the thing we see is that at very high values of viscosity, the dissipation is so strong that the jet is not able to form because of the very high dissipation, because of very high viscosity. Whereas at low values of viscosity, we see the formation of the jets and the droplets. There are other interesting facts. If you see here, this jet is quite thick, whereas this one is thin and it's fast. It happens because at small values of viscosity, so many capillary waves travel and they collide together to form a thick jet, whereas here, most of the capillary waves get damped because the viscosity is moderate, and that's why there is a cleaner collision at the base, which forms a thin jet. There is a slightly above this on the value of Onezor, there is a singularity at which the jet thickness is almost 0. The curvature and the velocity of the jet is infinite. So that is why we call there is a singularity observed here. So now this is what we saw for Newtonian cases. Now what happens when we add viscoelasticity? So just a small schematic diagram of how viscoelasticity is going to affect. So we have a liquid medium, we put polymers inside. Let's deform them. So we extend it, the polymers will get stressed. And since they are getting stressed, they will like to resist this formation. They can get compressed. Again, they will like to resist this. So the extra resistance force that is coming from the polymers that we will take as the stress is modulus times strain. So this A minus I is strain, where A is just an order parameter of how much you are stretching the polymers. It's also going to relax with time. So if you stretch the polymers and you wait enough, they will relax with time. And this is governed by this equation, which is time derivative of A depends on lambda. So the larger the lambda is, the larger time it takes to relax. And both of these combined together is what is called Oldroyd B. If you might have heard urologists using this term. So now we understand that both the modulus and the relaxation time changes the dynamics. And before we begin, we want to find out where the Newtonian limit lies in this parameter space, and they lie at both of the axes, but for very different regions. So when your modulus is 0, so no matter how much you are deforming the polymers, they don't have enough strength. Their strength is 0. So they will not apply any stresses. So it means you are Newtonian. If your lambda is 0, so it means that it relaxes immediately. So no matter how much you are deforming, it will relax immediately. So it will behave as if it's a Newtonian liquid. So long story short, it's a viscoelastic parameter space, and these axes are Newtonian limits. And as we go further from these axes, it will become more and more viscoelastic. So we start with the limit of Deborah infinite, which is known to be elastic solid. There is a very nice review paper on this by Jakob, where he like merges the realm of fluid mechanics and solid mechanics. So I will show you, this is just one simulation. The strength of the polymers, the modulus is still 0, but I will show you different components of A, and A is the deformation of the polymers that is dissolved. And the red colors will mean that they are being stretched, whereas blue colors means they are being compressed. So this is just one simulation. I'm just plotting different values of the different parameters, the different components of A. Now, if you look into the ZZ, this is huge red. So what this is signifying is that the polymers that are dissolved during the jetting, they are being highly stretched. And when they are being highly stretched, if they have some strength, they will oppose this stretching. And that is why if you add concentration of the polymers, they will suppress the formation of the jets. So this is why it happens, because the polymers that are dissolved are becoming like crazy stretched. Now we look into the space of viscosity and modulus. We start by looking two cases, same viscosity, we just increase the modulus. And there doesn't seem to be a lot of difference. I mean, both of them form jets and the droplets. But when you increase the modulus further to this yellow case over here, we see that now the strength of the polymers are much more, and now they are able to suppress the formation of the jets. So now in this case, the jets are able to form, whereas here they are suppressed.
What are you plotting in red? So this is a trace of the...
So this is a measure of how much elastic energy there is in this system. And the darker the region, the higher the values. So let us look into the details. For that, I plot the length of the jet. So the length of the jet increases and then decreases. So just to compare between two cases, I plot the maximum length of the jet that we see, and that we plot in this space of Onizog and modulus. So this is the value of the jet. So the lighter region means they have higher values. So we already understood that that we will have large jets when the viscosity is small, and as we increase the viscosity, because of the dissipation, we will have smaller and smaller jets, and after this value, this critical value, we will stop seeing jets. This is what we discussed in the first 3 videos. Now, similarly, as we saw in the case of viscosity, as we increase the modulus, we will the jet length will keep on reducing, and after this critical value, we'll stop seeing jets. And the value of the elastic number is very small. So this can be achieved by adding small concentration of the polymers into the system. Now, until now I talked about this limit of Deborah infinite, which was perfect memory. It's like a elastic solid. Like what happens if the polymers have finite memory? So I show you 2 cases. One has a finite memory and one has an infinite memory. It's like elastic solid. We see that the case which has infinite memory, there they are able to suppress the jets, whereas in this case, the jet and the droplets form. Why this is happening is because if you see this region, the elastic energy stored is almost nothing. It's all white, whereas there is red. So what is happening as the polymers are deforming, they are quickly relaxing. So they are not applying as much as resistance compared to this case. And that's why we are able to see droplets and the jets in this case. So to summarize everything, we look into this parameter space of elastocapillary and Deborah. The results that I'm going to show you have come from running thousands of simulations. And beforehand, we can kind of predict that if we have a large values of these numbers, if we have larger modulus and we have larger value of lambda, we will be able to suppress the jets. And this is exactly what we see. So this pink region observed at the large value of G and lambda is the region where we stop or we suppress the jets. whereas in the blue region, we see the formation of jets. But the interesting thing is the way in which the transition is happening. So at large values of lambda, the transition is happening at a constant value of g or elastogravity, whereas at small values of lambda, it is happening at a constant values of elastogravity. Now, why does this happen? So at large value of lambda, so it's at large value of lambda, the medium behaves as if it's elastic. So I'm talking about a viscoelastic parameter space, and at large value of lambda, it behaves as if it's elastic because the transition is governed by constant value of g. Whereas at small values of lambda, the transition is governed by this scaling, which gives us polymeric viscosity. So at small values of lambda, transition is happening at a constant value of polymeric viscosity, whereas at large values of lambda, it is happening at a constant value of elasticity. So in a way, this is a viscoelastic parameter space. Here it's viscous-like transition, and here it's elastic-like transition. We went on into details in our paper. We understand how these scalings come from. So basically, we started with slender jet equations. We found out the stresses at the base of the jet, and the elastic stresses were behaving as if they were viscous-like stress. That's why we get the transition at a constant value of polymeric viscosity. So now to summarize the first part, when you have larger concentration, larger values of modulus and relaxation time, you will suppress the formation of the jets, and the concentration required is very small. And there are two ways in which the transition happens. At large value of lambda, it happens at a constant value of g, whereas at small values of lambda, it happens at a constant value of polymeric viscosity. Now this
So could you address, when you go one slide back, perhaps you address why the function of Ohnesorg P is non-monotonic, this function of dipole. I mean, you explained these limiting cases that it is independent of dipole for small dipole and linear for large dipole, but you didn't address this.
So we have two limits.
Perhaps you address this a little bit.
Yes, I mean, so I think it's better clear in this plot. So we have two limits. In the small limit of values of lambda, we have this linear scaling. This is the eta p constant or Ohnesorg P constant. And at large values of delta, we have this constant value of elastogravity. Now in the between, there is this transition zone where it is shifting from this scaling to.
Yeah, but why? I mean, why non-monotonic? I mean, it's pretty remarkable because normally you would expect that it shifts monotonically, right? I mean, that it would go like this and up, but I mean, it goes like this, goes down, and then it goes up. So.
I mean, I did.
I mean, it's non-trivial, but I mean, perhaps you speculate a little bit.
I mean, I did ask to Gareth McKinley about this. You cannot find like any. I mean, he said. I mean, he had some deeper understanding about this. He said there is some exponential thing happening here in this transition zone. That is why it is creating some non-monotonicity.
But I mean, it's in the equation. I mean, in principle, you should be able to figure this out. I mean, we haven't, but it's
well, the short answer,
it's in the equation.
Yeah, the short answer is that we don't know, but the speculation is something else. So, I mean, it's probably residual elastic stresses that are there. But yeah, the short answer is we don't know.
Yeah.
So it's still an open
But
question.
I think it's good to address this and not to put this under the rug. So yes.
So this we published in our GFM. We also went on into more details about the droplet size we are having and about the other things. So this was about the droplet coming from the jet-like structures. Now there are also droplet coming from these bag-like structures, and that we call bag-mediated metamorphosis. For that, we are also running simulations. So instead of looking at this complicated system, we just take one droplet, put it inside a uniform flow, and let the flow create a bag, and then it ruptures. So this is ongoing work. We have already extended it to viscoelasticity. Alvaro and Tommy, they are conducting experiments on this, and we will compare our droplet distribution that is coming from here with experiments. One big question that comes from bag breakup is, as you will see, so as bag they expand, there are formation of holes that you see over here and over here. So the question is, how do these holes form? Yes.
So in your the simulations, you are trying to focus on the small scales where initially these jets and holes form.
Yes.
How much is the initial impulse reflected here? In the sense, if you change the initial impulse, you might get different number of droplets or holes. But each individual dynamic doesn't gets back to the initial input, or it doesn't matter.
So in the simulation, I have given a uniform airflow.
Okay.
So at time t is equal to 0, uniform airflow start. So you are saying impulse, so it means,
Yeah, like it's
so like
some sort
the,
of pulsatile thing, right? Because what we get is a real cough.
yeah, so it's the real cough, it happens in, so it's like, I think 200 milliseconds. So it's a, like the volume flow rate increases in 200 milliseconds and then it decreases.
Yeah, so that does this scope matter
Yes, it
in the
matters.
final answer?
Yes, yes,
Okay.
it matters a lot. Here, just for simplicity, I mean, the final experiment that the final numerical simulation that we'll do, we'll put the exact cuffing, this volume flow rate in the system so that we match well with the experiments. So now when we just focus on the one bag, we see that the holes are forming. And this is a very crucial step because if the holes were to form later on, then the bags would have been stretched a lot and the droplets that will come out will be much smaller. And the question, one of the biggest question is how do these holes form? There have been some hypotheses for this. They can form because of thermal fluctuations or van der Waals forces, but they don't apply here because the sheets there are of micron size. So these are much thick, like they are very thick to be able for these forces to break them. So there are two other prevalent hypotheses. Let's say we have some hydrophobic particle, dirt particle, or some bubble inside of the sheet, which will be able to break up when they are micron sized. Or we have some surface tension inhomogeneities. So we have some particle, some impurity. Because of that, there is locally a smaller value of surface tension. Because of it, these holes that you see they form. So we look into the second system where we put bubbles inside of the sheet, and we see how these bubbles are going to form holes. So we see there are again to able to mimic this cuffing, so that the air inertia which is making these sheets which is expanding the sheet, we put an acceleration, radial acceleration. So it's like a radial free fall, which is omega square r. So from here we get dimensionless parameter. First is omega, dimensionless viscosity, bond, because there is a radial acceleration involved, asymmetry of the bubble, and other parameters which we keep constant to air water systems. So now the sheets that we see, it's not just seen in our cuffing and sneezing, it's also seen in a lot of other applications such as inkjet printing, spray cleaning, pesticide spray cleaning, and so on. But only thing that determines is how much driving is there and how viscous are these sheets. So the question is, how do these sheets break? And for that, we start by looking into two cases. With same viscosity, we increase the driving. We see that when the driving is strong, when the driving is small, even if the bubbles have managed to cause the holes, they come back and then they heal. Whereas if the driving is strong, when the hole forms, it opens up. So it is clear that you need strong enough driving to be able to break the sheets. And it is also seen in experiments where you see the holes are formed and these holes are healed when the driving is small. Whereas in other cases, when the driving is strong, these holes, they open up. So we look into the space, we look into, we do all like 300 simulation, we see that the strong driving is required to open the sheets. But there is a different behavior. At small values of viscosity, it happens at a constant value of driving, like a constant value of bond. Whereas the driving, it has some kind of scaling. So we wanted to understand what sets these transitions. And for that, we look into the completion of the time that is taking to collide and the time it is taking to expand. So first is the collision time scale, so the time taken from the sheet to go from a state like this to a state like this. And that we, at small values of Fonizol, we can do a basic simple scaling argument. So the driving here is the capillarity. So capillarity is the driving that we balance at small Fonizol with inertia, because when viscosity is strong, inertia is the only thing that is resisting, which gives us the time scale, inertia capillary time scale. Whereas at large values of Fonizol, we balance this capillary driving with viscous stresses, which gives us the time scale, viscocapillary time scale. If we see the scaling law, at small values of anisor, we will have this inertial capillary time, and at large value of anisor, we will have this viscocapillary time scale. When we put our simulation results, it matches perfectly, no matter what the value of bond we have. So it is irrespective of bond, and we have a consistent results with our scaling. Now these values we compare. So this was collision time. This we compare with retraction time, and at small anisor we get the scaling constant bond, and at large value of anisor we get the scaling of 1 minus half. And when we plug this scaling here, we find a perfect match. At small values of anisor, this completion in time scale gives us constant bond, whereas here it gives us a scaling of 1 minus half. Now from this scaling, if one were to ask the question, what happens for vanishing driving? So if we were to relate with cuffing, what if you are not cuffing but you are speaking, or what when you have a liquid sheet and you are not driving, what will happen in that case? So in that case, when bond is 0, the scaling suggests that the critical anisor will be infinite. So no matter how viscous you make the sheets, they will always heal. That is coming from this, the scaling predictions. We see the same thing in simulations. No matter how much viscous we make the sheets, they might take a very, very long time, but they always heal. This is also we saw in the simulations. Now, there is third prediction also. It is a very famous paper by Taylor, where he had a sheet and he created the holes by putting air jet or needle. And he used, so we have been using dynamics, equation of dynamics and simulation. Instead, he used energy arguments. So he used like energy. Sorry, Taylor and Michael, they both used energy arguments of the initial sheet, and if you are to create a hole, and then they find out the energy difference, and based on which they predicted, which we call Taylor and Michael geometric criteria. So they predicted that if your holes are, so this is hole over thickness of the sheets. So if you have a large hole, the holes will open up, otherwise they heal. And they didn't, like, it's the only criteria they have. It's only a geometric criteria. So it doesn't really depend on viscosity, but mind you that this relationship is only valid when dynamics is not included, because we are talking about energies, and it is only applied when dynamics is not included in this energy equation. So what if the whole geometry were to change? And if it changes, how can it change? If there is a delay in breakup, which in physical system can happen when you have impurities such as surfactants. So let's say if you have surfactants, and let's say your bubble is put inside of the sheet, so it might break up at a later time because there are surfactants here. Let's say it might break when the system is like this. And earlier the holes were healing, and now because of the delayed breakup, they might open up. So we included this into account. We put this theta, the hole opening angle, as our initial condition, and we look into these cases in our space of anisor versus theta. We see the yellow case, the small hole opening. We see two cases with small hole opening angle and with large hole opening angle. We see that the small hole opening angle case heal, just like it was healing before, whereas the large opening case, it opens up. So now once again we see in this space, we again do a lot of simulations, and we found out that large opening cases, hole opening cases, they open up, otherwise they heal. Now here there is one interesting aspect. At large values of anisor, the transition is happening at a constant value of theta, whereas as we decrease the value of viscosity, it needs larger and larger theta to open the sheets. So how does this happen? Because if we compare our system, so when anisor is large, viscosity is very high, and there is no dynamics. So whatever is coming from capillary, which is the driving, it's directly going into the inertia. Because of viscosity is very high, so there is almost always no inertia. I'm sorry, whatever is coming from the capillary driving is going directly to viscosity. Everything is dissipated, and there is no inertia. So this system, like the high anisor cases, is exactly the system studied by Taylor, and the criteria there is match as well. But as we decrease the value of anisor, inertia comes into the picture, and we need larger and larger theta to be able to open the sheets. So just to summarize everything, we need larger opening angle, larger deformations to open the sheets. We saw that at large values of onisol, we need this is happening at a constant value of theta. We need stronger dragging to open the sheets, and that even when the viscosity is vanishing, we need a constant value of bond to open the sheets. Now, there was a very nice commentary paper by Hitler, where he hypothesized that we need double threshold behavior. So we need strong enough dragging and large enough distortion to open the sheets. And this behavior is not just limited to breakup of sheet. It is also seen in other fluid dynamics problems. So if you have a pipe flow, and if you see the transition from laminar to turbulence, that happens when there is strong enough driving. So when Reynolds number is large, and when there is large enough distortion. Also in viscoelastic turbulence, you need large enough Weisenberg number and large enough distortion, and which is also seen in our case, that we need strong enough driving, like strong enough driving here, and large enough distortion to open the sheets. So until now, I discussed the case where the holes were formed by presence of bubbles. Now let's see what happens when there are some chemical or temperature inhomogeneities involved. So for that, first we create a sheet, and that we do by putting a tap below a spoon, which creates a sheet. And now we have to modify the surface tension locally, and that we do by putting an ethanol droplet in the sheet. So this experiment Prashant is doing. When we do that, when we look closely to the region here, we have a liquid sheet. Locally, so this is, I'm plotting surface tension. So locally, the surface tension is low, and far away, it's water surface tension. So locally, its surface tension is low because of ethanol droplet that is present there, and far away, surface tension is high. Now, this is the system that we want to study, and there we get three dimensionless parameters. So first is the gradient, that gamma R over gamma naught. Second is our onisol, and the third is our Peclet number. If we see this parameter space between gradient and Peclet number, let's say we see two cases with same values of everything, onisol and gradient, and we just change the value of Peclet number. So this is the small Peclet number case, and this is the large Peclet number case. We see that in small Peclet number case, the diffusion time is low, so the ethanol diffuses immediately, and it is not able to break up the sheet. Whereas when the Peclet number is large, we see that the diffusion time is less, so the gradient stays there, and it is able to break up the sheet. So this is also an ongoing work. There are many theoretical arguments which we can find for this case, for how the thickness is evolving in these cases based on the values of Peclet number and gradients. And we will also get the experimental results, and we will be able to piece together everything. So just to summarize everything, I talked about sneezing. There are two ways in which the droplets come out. They come out from these jet-like structures, so which we understood by modeling as bubble bursting jets. And the second is they break by these back breakup. So these sheets, that is for taking the back breakup form. And when do these sheets break? There are two main hypotheses that we had. First, because of the presence of the bubbles, which we saw, and second, because of the presence of surface tension inhomogeneities. So that would be all, and I thank you all for your attention, and I'm happy to take any questions.